In mathematics, a bijection, bijective function or one-to-one correspondence is a function between the elements of two sets, where every element of one set is paired with exactly one element of the other set, and every element of the other set is paired with exactly one element of the first set. There are no unpaired elements. In mathematical terms, a bijective function f x y is a one-to-one and onto mapping of a set X to a set Y. A bijection from the set X to the set Y has an inverse function from Y to X. If X and Y are finite sets, then the existence of a bijection means they have the same number of elements. For infinite sets the picture is more complicated, leading to the concept of cardinal number, a way to distinguish the various sizes of infinite sets. A bijective function from a set to itself is also called a permutation. Bijective functions are essential to many areas of mathematics, including the definitions of isomorphism, homeomorphism, diffeomorphism, permutation group, and projective map. Definition: for a pairing between X and Y to be a bijection, four properties must hold. Each element of X must be paired with at least one element of Y. No element of X may be paired with more than one element of Y. Each element of Y must be paired with at least one element of X, and no element of Y may be paired with more than one element of X. Satisfying properties and means that a bijection is a function with domain X. It is more common to see properties and written as a single statement. Every element of X is paired with exactly one element of Y. Functions which satisfy property are said to be onto Y, and are called surjections. Functions which satisfy property are said to be one-to-one functions, and are called injections. With this terminology, a bijection is a function which is both a surjection and an injection, or using other words, a bijection is a function which is both one-to-one and onto. Examples: batting lineup of a baseball or cricket team. Consider the batting lineup of a baseball or cricket team. The set X will be the players on the team and the set Y will be the positions in the batting order. The pairing is given by which player is in what position in this order. Property is satisfied since each player is somewhere in the list. Property is satisfied since no player bats in two positions in the order. Property says that for each position in the order, there is some player batting in that position, and property states that two or more players are never batting in the same position in the list. Seats and students of a classroom. In a classroom there are a certain number of seats. A bunch of students enter the room and the instructor asks them all to be seated. After a quick look around the room, the instructor declares that there is a bijection between the set of students and the set of seats, where each student is paired with the seat they are sitting in. What the instructor observed in order to reach this conclusion was that every student was in a seat. No student was in more than one seat. Every seat had someone sitting there, and no seat had more than one student in it. The instructor was able to conclude that there were just as many seats as there were students, without having to count either set. More mathematical examples and some non-examples. For any set X, the identity function 1x, xx, 1x equals x, is bijective. The function f f equals 2x plus 1 is bijective, since for each y there is a unique x equals 2 such that f equals y. In more generality, any linear function over the rails, f equals x plus b is a bijection. Each real number y is obtained from the real number x equals a. The function f given by f equals arctan is bijective since each real number x is paired with exactly one angle y in the interval so that tan equals x. If the codomain was made larger to include an integer multiple of pi 2, then this function would no longer be onto since there is no real number. which could be paired with the multiple of pi 2 by this arctan function. The exponential function, g equals x, is not bijective. For instance, there is no x in R such that g equals -1, showing that g is not on 2. However, if the codomain is restricted to the positive real numbers, then g becomes bijective. Its inverse is the natural logarithm function lane. The function r plus h equals x2 is not bijective. For instance, h equals 1, showing that h is not 1 to 1. However, if the domain is restricted to, then h becomes bijective. Its inverse is the positive square root function. Inverses. A bijection f with domain x also defines a relation starting in y and going to x. The process of turning the arrows around, for an arbitrary function does not, in general, yield a function. But properties in of a bijection say that this inverse relation is a function with domain y. Moreover, properties and then say that this inverse function is a surjection and an injection, that is, the inverse function exists and is also a bijection. Functions that have inverse functions are said to be invertible. A function is invertible if and only if it is a bijection. Stated in concise mathematical notation, a function f xy is bijective if and only if it satisfies the condition for every y in y there is a unique x in x with y equals f. Continuing with the baseball batting lineup example, the function that is being defined takes as input the name of one of the players and outputs the position of that player in the batting order. Since this function is a bijection, it has an inverse function which takes as input a position in the batting order and outputs the player who will be batting in that position. Composition. The composition of two bijections f, x, y and g, y, z is a bijection. The inverse of is. Conversely, if the composition of two functions is bijective, we can only say that f is injective and g is surjective. Bijections and cardinality. If x and y are finite sets, then there exists a bijection between the two sets x and y if and only if x and y have the same number of elements. Indeed, in axiomatic set theory, this is taken as the definition of same number of elements, and generalizing this definition to infinite sets leads to the concept of cardinal number, a way to distinguish the various sizes of infinite sets. Properties. A function f R is bijective if and only if its graph meets every horizontal and vertical line exactly once. If x is a set, then the bijective functions from x to itself, together with the operation of functional composition, form a group. The symmetric group of x, which is denoted variously by s, sx, or x. Bijections preserve cardinalities of sets. For a subset A of the domain with cardinality A, and subset B of the codomain with cardinality B, one has the following equalities. F equals A and F minus 1 equals B. If x and y are finite sets with the same cardinality, and f, x, y, then the following are equivalent. F is a bijection. F is a surjection. F is an injection. For a finite set S, there is a bijection between the set of possible total orderings of the elements and the set of bijections from S to S. That is to say, the number of permutations of elements of S is the same as the number of total orderings of that set, namely, n. Bijections and category theory. Bijections are precisely the isomorphisms in the category set of sets and set functions. However, the bijections are not always the isomorphisms for more complex categories. For example, in the category GRP of groups, the morphisms must be homomorphisms since they must preserve the group structure. So the isomorphisms are group isomorphisms which are bijective homomorphisms. Generalization to partial functions. The notion of one-one correspondence generalizes to partial functions, where they are called partial bijections. although partial bijections are only required to be injective. The reason for this relaxation is that a partial function is already undefined for a portion of its domain, thus there is no compelling reason to constrain its inverse to be a total function, i.e., defined everywhere on its domain. The set of all partial bijections on a given base set is called the symmetric inverse semigroup. Another way of defining the same notion is to say that a partial bijection from A to B is any relation R with the property that R is the graph of a bijection F, A, B, where A is a subset of A and B is a subset of B. When the partial bijection is on the same set, it is sometimes called a one-to-one partial transformation. An example is the Mobius transformation, simply defined on the complex plane, rather than its completion to the extended complex plane. Contrast with, this list is incomplete, you can help by expanding it. Multi-valued function.